everyone, this is going to be the final video on that full reimplementation of the latent diffusion model. Again, as a quick recap, in the previous video, we basically implemented and trained this pipeline, right? So something that trains our variational autoencoder, because the goal of the VAE is to essentially take images from the pixel space, project them to some latent space, some much smaller latent space. So as a quick recap, our original images were 3 channels by 256 by 256. Our latent space is 4 channels by 32 by 32. That's kind of a hyperparameter, right? How small do you want the spatial dimensions to be? How many channels do you want in the latent space? It's completely up to you. You can kind of mess with it however you want. And so we trained this model, and to train this model, we had to essentially add on additional losses like the LPIPS loss and the patch-GAN loss, just to make sure the perceptual quality of the variational autoencoder, the reconstructions that the VAE produced, were high quality, right? So that was essentially the endpoint of the last video. But latent diffusion models don't end there, because we haven't done any diffusion yet. In this system, right, all we've done is train something that can faithfully take an image, compress it, and decompress it, and we're good to go. But now what we want to do is train the diffusion pipeline on the latent space. Now, again, the prerequisite to this is, of course, my diffusion video, because the code actually isn't all that different from that diffusion video, and I'll be using some parts of it here as well. I'll point that out when we get there. But what the pipeline will look like is kind of like this. Basically, during training time, we're going to take an image, we're going to compress it down. We are doing text conditioning, so text conditional image generation. So we're going to ask our UNet here to take the latent representation, its corresponding text conditioning, and then do the diffusion stuff that we've already learned about earlier, right? And once we do that, it's going to produce an output, and then this will go back to the over here, and we're good to go. We don't really care about this portion right now for training. So during training time, all we really need is to take images, compress them, and then this is essentially the target, and the diffusion process is to take this tensor here, add noise to it, t steps worth of noise to it, and then denoise it using this UNet. And that's essentially it. And of course, conditioned on the text conditioning, right, from our clip model. And so that's what we're going to be building. During inference time, what we do is we generate noise right here, denoise it 1,000 times, or however many time steps we have in our diffusion process with the text conditioning, and then this will be passed to the decoder. So during training time, we really care about the encoder. Once we're done training, all we really care about is the decoder. So we'll see all that come together as we build the pieces. So there are a couple things that we're going to need to do, but of course the first place we need to start is this UNet. And we're going to be following the diffuser's UNet 2D as close as possible, just so the code is, relatively one-to-one. To do this, we're going to need to do one thing. In the previous video, what we did, so let me make this a little bit bigger. In the previous video, we implemented a transformer, but we didn't actually implement a transformer. We just implemented the attention mechanism. And that's kind of all we needed for the variational autoencoder, and we're good to go. In the case of the UNet actually uses full TransformerBlock. So it doesn't just have attention, but it also has like the feedforward layers and all the other good stuff that transformers typically have. So let's go ahead and start there, right? Let's implement the remaining pieces of the transformer. And then once that's done, we'll be able to essentially go on to implementing the UNet. We have the attention mechanism. We just need the rest of the pieces of the transformer. So the first thing we're going to do is implement the activation function. Now, in standard transformer fashion, you use the GEGLU activation function, but in the UNet here, they seem to use GEGLU. And GEGLU is essentially just a gated GLU. So it's pretty straightforward. What we're going to do is basically GEGLU and then module def init self. And it's going to take some dimension in, dimension out, and a bias if we want it. Super GEGLU self.init. There we go. So GEGLU is pretty easy. It's just a linear layer. So we're going to do self.proj and then dot linear from dim in to dim out times 2. And bias equals bias. And we're going to do forward self x. And this is basically what a gated activation function is. A normal activation function, you basically take some x and it goes through some activation function f of x and it gives you some output. And that's basically it, right? That's every active, I mean, that's every function, right? Let's X out there, every function. On the other hand, a gated activation function does this. Given x, we're going to pass it through two different functions, right? Let's say f of x and g of x. And this is going to give output 1 and output 2. And with these two outputs, we can then apply an activation to one of these. Like, let's say we're doing, in this case, we're doing GEGLU, but it could also be sigmoid or anything else, GEGLU, to one of them. And then we multiply them against each other. And this GEGLU, remember, this GEGLU essentially it looks kind of like a ReLU, right? So it's close to 0 when you're less than 0, and then it's, greater than 0 when you're greater than 0, whatever it may be. So let me just pull that GEGLU picture up right here, right? Standard GEGLU activation, just like this. But if I have something like this, if we look right here, if this value, if the output of this thing is essentially a function that looks kind of like this, then when I multiply it to something like my O1, the first output of the first part, all we really are doing is modulating, right? So this is essentially a gate that decides which parts of O1 stays, and which parts of O1 goes away. So things that go away will get multiplied by values that are close to 0, right? This stuff right here. Things that stay will get multiplied by something over here. And that's basically it, right? That's essentially the gating function. It allows our activation function to modulate which information goes forward and which information stays. You could also do you could use a sigmoid function or really anything else. There's all sorts of activation functions you can use, and this has become a very popular way of doing gated activations. Gated activations have become actually pretty popular in a lot of LLMs because it allows for more fine-grained information to flow through. Like the model gets to decide what information is important, keeps going, what information is not important, doesn't keep going. Kind of like a recurrent neural network, right? Like the LSTM gating scheme and all that sort of stuff. And so what we're going to do is, I mentioned there's two functions. Instead of doing, technically, we could have two linear layers, one for the data and one for the gate, like self.gate. Both of them would be from dim in to dim out. But instead of doing two separate linear layers, which is a little bit slower, we can fuse them into one layer and then chunk the results afterwards. So we're going to do hidden states, and then gate is going to be hidden states dot chunk 2 dim equals -1, right? So along the last dimension, because these are linear layers, you're going to take some dimensions by input size, it's going to produce some output size, and we're just going to chunk that output size like this, and then we can return hidden states times f dot GEGLU gate, right? So again, this is going to modulate what information from this hidden states will go forward and what information does not go forward. This allows for more finer control in the model. After that, our feed forward should be very simple. nn.module def init self, and this is a standard transformer, right? So you'll have the input dimension, the dim mult, right? Typically 4. So you know how much do you want to do the increase the projection by. Dropout we'll set to 0.0, and bias we'll set to true if we want it. And so then our hidden dimension will just be the dimension times the dim mult. Make sure it's an integer, right? And then we can do self.fc1 GEGLU. So basically the first linear layer is going to be essentially this. It's going to be our GEGLU layer right here. So it's going to be a GEGLU dim, hidden dim, bias equals bias, just like that. So this is basically that projection that's going to control what information goes forward and what information stays. And that's basically it. Self.drop, we'll have a dropout layer, and nn.dropout. This is going to be the MLP dropout, no problem. And then self.fc2 is going to be nn.linear, hidden dim to dim. Just go back. Because again, at the end of this, the shape will be just dim out, not dim out times 2. So the shape will be hidden dim, and we're good to go. So essentially what it's going to happen is we're going to go from batch by input, and we're going to go to then batch by 2 times output, right? 2 times output. And that's going to become actually not just one batch times 2 by output, but that's going to become essentially we split them, chunk them into something like this of batch by output. And we're going to multiply it by something else that goes batch by output that we applied the GEGLU to, right? GEGLU activation to. Let's put a little space right there, just so it's clear. And there we go. Yeah. So the final shape will be essentially just batch by output, right? Because we're just multiplying a batch by output by a batch by output tensor. And so that'll be basically the hidden dim is the output. And so the last layer will go from hidden dim back to the original dimension. So we're good to go for the transformer, right? Now that we have that, we can do def forward, and we can do x is self.fc1 GEGLU x is self.drop x, and x is self.fc2 x return x. So yeah, normally we just have a normal, we basically do a linear layer followed by a GEGLU activation, but now we're doing a linear layer with a gating scheme followed by our, a second linear layer. So that's all that's changed. Nothing too different. So let's go ahead and write a basic transformer block 1D, and then we're going to essentially wrap this to make it a transformer block 2D, and we'll see exactly what that works out as. I'm going to go through this pretty quickly because it's a standard transformer block, and we already did the hard work earlier, right? When we UNet.module. So we have all of our standard setups for our transformer block, and then remember, in our UNet, in our intention implementation, when we're implementing it for the variational autoencoder, we actually did a little bit of extra work. For the VAE, we only needed self-attention. But for the UNet, we need cross-attention because we have both images and context. So we'll be actually using this part of the code today for the UNet, essentially, to do our cross-attention with the text conditioning that we'll be passing in later. Super.UNet. We specify that right here, right? The cross-attention dimension, whatever it may be. So it's whatever the clip model is. I think it was 1024 or something like that. I can't remember. It might have just been 768. Cross-attention, self.cross-attention dim is going to be cross-attention dim. And then we're just going to do our standard stuff. So I'm first going to do a self.attention. Self.norm1 is going to be nn.layer norm from embed dim with the norm EPS, whatever we set it to. And we'll just self.attention1 is going to be our attention mechanism that we've already spent all this time implementing. Right, so this is the attention mechanism that's going to do our self-attention. After we do self-attention, and this is self-attention on the images in our UNet. So the first attention block is going to do only attention on the images of the UNet. Now, what we're going to do is follow it up if cross-attention dim is not none, right? So if this is a transformer block, which it will be for the UNet, if this is a transformer block that will also be doing cross-attention because we're doing text conditioning for some reason, then we're going to do self.norm2. It's going to be again nn.layer norm, embed dim, norm EPS, and then we're going to do attention 2. And this second attention, you can see cross-attention dim is not none here. So here it's none, which means this attention block will be treated as a self-attention layer. So this is image self-attention. The second one will be image text cross-attention. So this block is supposed to learn how is the image patches related to other patches in the image, and this block is supposed to learn how are the image patches related to the token embeddings from our context. And that's basically it, right? Nothing too crazy. And both of these are set to false. So again, I'm trying to make it as similar to our, the implementation from Hugging Face, from the diffusers package. So that's why I've picked these parameters. I'm sure you could mess with them and tune it for your own model. After our transformers, we just need our feedforward layer, right? So I'm just going to paste that in. Just type it again, right? Feedforward, just as another normalization and a feedforward layer, and we're good to go. Def forward self x, context is none, and attention mask is also none by default. And so let's go ahead and start. So first it's going to be norm hidden states. It's going to be self.norm1x, right? So it's going to go ahead, take the images essentially, normalize them. And then our attention out is going to be self.attention1 norm hidden states. And then x is x plus attention out. So that's going to go ahead and do a residual connection. So this is us passing data through self-attention on just the image. And there we go. That's all we need. After that, if self.crossAttentionDim is not none, so if we are doing something, we're going to raise a quick exception right here. So if cross-attention's_dim is not none, but if context, if we don't actually pass in context, then we kind of have an issue, right? We're just, this is a block that expects context, but is not getting any context. So we want to avoid that, right? We don't want to do that. There we go. And then norm hidden states, just like before, hidden states is going to be self.norm2x, and then attention out is again self.attention2. But now it's going to take our norm hidden states, the context, and the attention mask, right? All three of these things will be passed in. And again, x is equal to x plus attention output, just like that. Finally, we have the feedforward layer. I'll just paste this in again. There we go. So we have our normalization, we have our feedforward layer, this stuff, and then we return x, and we're done. And this is a standard basic transformer block, and I'm going to call it basic transformer block 1D. Because remember, in our previous video, we talked about how images are technically 2 dimensions, right? Batch by channels, by height, by width. So there's a height and width dimension. Transformers typically process data in the shape of batch by sequence length by embedding dim. So we can take an image, batch by channels by height by width, and reshape it to batch by number of patches, which is height times width, right? Like how many locations do we have? There's height times width locations, by channels, which acts as an embedding dimension. I did not handle any of these cases right here. This transformer block just assumes the standard batch by sequence length by embedding dim shape for everything, right? Because we're just doing wrappers on methods we've already written earlier. But of course, we're working on images, so we just need to do one more quick check right here. So we're going to do class TransformerBlock 2D and end.module. And I'm going to copy in all of this stuff again, same as before, just our init, right? Number of attention heads, head dim, all that stuff, just like what we had, a lot of stuff that we had earlier. And what we're going to do is super.init, and we can do self.projdim is equal to num attention heads times attention head dim. So this is kind of the first step. We didn't really talk about any kind of we didn't really set any multi-head attention or anything like that here. All we just have is what is the head dim that we want, which I just set to 1 for default. The actual attention heads, or basically the actual head dim, will be the number of attention heads by the head dimension. So that's what we want to project our data to, so we can do that. Because remember, our data right now is batch by, right now it's going to be batch by channels, by height, by width, and we'll kind of follow the shape as we go. So this is the data coming in. So I'm going to put that right here. And we'll kind of get back to the importance of that in just a second. Self.norm is going to be norm is nn.group norm num groups is equal to group norm groups. Num channels is equal to in channels, and EPS is norm EPS. That's the standard group normalization. And the first thing we need to do is this. We're going to do our project batch. So basically project this, right? Project this. And we want to project it to be by projdim by height by width. So our channel dimension is whatever it is coming in. We don't really know. I mean, we do know, and we'll set that in a bit. But it's whatever that's coming in. And what we want to do is just make sure we project it correctly. So in channels is what's coming in, but what we want is projdim, whatever this projection dimension is, right? Because this is going to become the embedding dimension in just a second, right? So we want to make sure this is all correct. So the first thing we're going to do is self.proj in is going to be nn.conv 2D, because it's an image, right? This is just a standard image tensor. All we want to do is map channels to projdim. That's it. So we'll have in channels is going to be in channels, and our out channels is going to be self.projdim, which has which will be in the future split into how many heads we want and the dimension of the head that we want, right? So that's basically it. Like for example, if proj_dim, if we made it 768 and we asked for 12 heads, each with 64 embeddings, right? So all we're doing is, instead of typically in transformers, we set that it's 768 and the number of heads, and then this has to be divisible. In this setup, we're just saying I want 12 heads with 64 dimensions per head, which I know multiply to the 768 that I want. So it's just kind of the other way around, but it doesn't change anything. We obviously want to make sure we don't change the height and width dimension here. So we're going to do kernel size is 1, stride is 1, and padding equals 0. So it's going to be essentially a 1x1 kernel size thing. So now we have our transformer blocks, self.transformer blocks, or let's just do transformer as nn.module list. And this is going to be that basic transformer block, right? The thing we just implemented above, basic transformer block. And it's just going to be however many I specify, by default 1, but of course you can increase it more to increase your model capacity and complexity, right? And each of these, so just to kind of go back around, so basically we took this data, we projected it, the channel dimension, to the dimensionality that we wanted. That happened right here. Now, what about the conversion from all of this? So we kind of talked about, oh, we need to go from batch by channels by height by width to the batch by height times width by channels, or also in cross attention, same thing. Where did this happen? Well, that actually happens in our attention mechanism. Remember that we wrote these methods, check for reshape, where check for reshape is using our image to sequence method that we wrote right at the very top, right? This is the thing that takes data and converts it to the correct shape, the shape that our attention mechanism expects it in. And so that's it, right? So nothing too crazy. Obviously I can't recap everything, but if you are watching the videos in order, then it should make quite a bit of sense. Okay, so now that we have that, we need to make sure we took our basically image tensor here and projected it up to our proj_dim, but we want to make sure the output is the same shape. So we went from in channels to proj_dim, right? So in channels to proj_dim. Now we're going to go from proj_dim back to in channels. We're just going to put it back how we found it. So self.proj out is going to be nn.con 2D in channels. Remember, in channels is going to be self.proj_dim. That's where we're at right now. Out channels is going to be in channels, right? That's the original in channels, what came into this block. And everything else is the same. Kernel size 1, stride 1, padding 0. That's it. So let's do our forward method now. Pretty straightforward. So it's going to be self x will have context, none by default. Attention, mask, also none by default. So x is going to be self.norm x, and then x is going to be self.proj in x, and that's going to go ahead and do our projection, right? So we normalized, we projected it to the right dimensionality. Now that we have that, we can go ahead and do our transformer step. So this is going to be first, it's kind of up to us. We can either flatten to a 1D signal right here and pass it to the transformer, or we can just give it to the transformer directly, and internally it will do the conversion. Let's just pass it in the right way, right? Just so it's super clear. So blank is equal to image to sequence. X, the second thing here, is basically the image to sequence returns x and the number of patches, right? Height times width. We don't really care about that because we're assuming everything is a square image anyway, so it's just a little simplification. So let's go ahead and just do it here. We didn't have to, but it's fine. This will be flattened to 1D signal, basically, right? So that does this conversion, right? Batch by embedding by height by width to batch by height times width by embedding. After that, we need to pass it through all the transformers. For block in self.transformer, we're going to do x is block, and we're going to pass in x, our context, and the attention mask. I keep spelling this wrong. Attention mask. There we go. And then x is going to be sequence to image. X, so we're going to take this back, and this is going to undo it. We're going to go from batch by height times width by embedding back to batch by embedding by height by width. So that's the second one right here. We have a quick sanity check here. We can pass in image dimensions if we wanted, in case it wasn't a square, but if we don't pass it in, we assume the images are square. And that is what we're working on, just square images. So we're going to keep it that way. So x is sequence to image, and then x is self.proj out x, return x. And that essentially completes our entire transformer block. So there's some of those comments that I just put in. Good. So that is everything we need for the transformer. Now that we have the transformer, I think we have everything we need to start our UNet, right? All right, so now that we have all of our kind of, these layers ready to go, we can go ahead and implement the UNet. And the UNet is, as always, not hard to implement. It's just kind of annoying. So we're going to go through it. I'm going to try to explain it to the best of my ability, and we will go from there. For a new class, we're going to need a couple things. So the way this is going to look is we're going to essentially have a down block, right? So a down block, and what a down block will have is multiple downsample or multiple residual blocks followed by and potentially transformer blocks, and potentially also a downsample block, right? So that's what we're going to do it or have it as. So let's go ahead and just get started. I'm going to paste in the function stuff. So type that. We're going to get rid of class conditioning from everywhere just to make it as clear as possible. And so there we go. We have all of this. Good. And so step one, we want to go ahead and create our layers themselves. So we're going to have resnets and then .module list and self.attentions and then .module list. Right, so the way this is going to work is every single down block will contain at least one resnet and potentially, pairs of resnets and attentions, and we're going to toggle through them. So what this is going to look like is like this. For I in range num layers, we're going to do in channels is equal to in channels if I is 0, else out channels. Right, basically at the beginning it's in channels, and every layer after that, if we have more, will be the first layer is going to go from in channels to out channels, and then every layer after that's just going to go from out channels to out channels over and over again. So there we go. And I'm just going to copy the rest of this in because I don't want to type all of it, but it's pretty straightforward. We're just we can delete these two because we don't have class conditioning. And what we're going to do is basically for every single layer, we're going to append a resnet and optionally append an attention block, right? And if there is no attention, then we're going to append none for simplicity. And so that's it. That's basically all it is. Every single layer or every single block will consist of multiple residual and transformer blocks. At the end of the down block, we actually need to do the the down sampling part. So we're going to do if self.add downsample. Right, so if we want to do downsample, no problem. We can go ahead and just add that in as well. Self.down sample is down sample block 2D. In channels is going to be out channels. Kernel size is going to be our downsample kernel size, and our downsample factor is going to be is equal to downsample factor. So essentially, all we're going to do is go through a bunch of these layers and then potentially downsample at the end. Okay, so let's write the forward method for this. Now remember, this is actually a UNet, right? So as we're doing our layers, right, we have a bunch of them here, we need to store those temporary outputs, right? Basically store those outputs. So in the upstream, when we're decoding, we can concatenate those things on. And this is where it gets more annoying. And we don't have to deal with it just yet, but we will in a bit. So we're going to do def forward self x. And remember, this is our UNet. So in the UNet, we're going to have time embeddings, but also we're going to have text conditioning. So we have time embed, right? So what step of diffusion are we on? But then we also have text conditioning by default none, and text attention mask also none. And what we're going to do is store them in something called skip connections outputs and be listed. We're going to do for I res attention in enumerate zip self.resnets self.attentions. We're going to do x is our residual block with x and the time embeds. And then if attention is not none, right? So if it's not none, then we're going to do x is also attention, x text conditioning, text attention mask. Go ahead and pass it to the TransformerBlock as well. And once we're done, we're going to do skip connection outputs dot append x. And lastly, if self.add downsample, if we do have a downsample, then we're going to do x is self.downsample x and skip connection outputs dot append x. And that's it, right? That's basically it. And we can do return x skip connection outputs. And that's all. Good. So downsampling is easy. After our down blocks, we also have something called mid blocks. Mid block will look exactly the same. So mid blocks are essentially this piece right here, this bottom chunk right here. So we have downsampling. Mid blocks are just a stack of some convolutions, and then we have our upsample blocks, right? So that's what we're going to do. Mid block to D and n.module. And again, everything in this method will be identical. So we can just paste everything, and actually nothing really changed from before, except for one thing, which I'll mention right here. Let's delete U2. Let's delete U2. The mid block always starts with a single resnet, at least, but we can then add on additional resnets if we want, depending on how many layers we want. There we go. Delete that. Good. So yeah, that's it. So the mid block is the same one resnet at the beginning, and then we're going to store attentions, and then we're going to, for every single layer, store another resnet and another attention, the same way as we did. And then in the forward pass, it's pretty straightforward. We have essentially always one resnet. So we can delete class conditioning because we don't have that. We're always going to have one resnet, so that's self.resnet0, and then we'll loop through the rest of them, resnet1 to the end and self.attentions, right? And then just pass it through the resnet, pass it through the attention, and that's it. So the mid block is nothing fancy. It's just like the down block, but there's no downsampling, right? So it basically is like the downsampling block without downsampling. So we could have reused the same code here. It just makes it look nice to have, it makes it just clear, right, to have these set up. Okay, so now let's implement our upBlock 2D. Our new class, upBlock 2D. This is where it gets more annoying. So I'm going to go ahead and just copy in, again, the function call right here. We don't need U2. And this is where it starts to get annoying. So I've already printed out some stuff here to make this a little bit easier to understand. But let's just go ahead and start from the top. Self.add upsample is add upsample. We need to basically create some resnets, resnets, and then module list, and self.attentions is nn.module list. Right? So I'm going to store those in there. And what we're going to do is basically we need to create a mirror image, right? A mirror image of our down block. So for every down block, there should be a reciprocal up block. The only thing that changes though is for every single block, we not only have the input from like our previous stuff, but we also have the residual connection, the skip connection that we're going to concatenate on. And so we just have to keep track of a lot of these shapes, right, as we're going. And this is what makes implementing UNETs just super annoying, but let's go ahead and do it. Let's pretend, so we're going to, or here, we'll look at that in a second. For I in range num layers, right? So if we have 2 layers in that one, then we're going to want 2 layers in this one. We need to know how many channels, right? How many channels are we going to be getting from our skip connections, right? The skip connections. So I've actually gone ahead and printed some out already. So let's just look at this real quick, just to make this clear. So every one up block will have its number of channels, 128, 256, 512, 1024, whatever they may be. This is just like in the VAE, right? 128, 256, 512, 512. We say each block of the VAE had this many channels. So in the same way, we have the first block of our up block will be 128, the second block will be 256, 512, 1024, just how many channels we have, right? So our residual connections will have the number of channels of the next block. For example, if this is our setup, then the outputs of the encoder will look like the following. And this assumes we have 2 layers per block. So here's the 128 by 32 by 32 input. And then we're going to have basically 2 blocks at 128, right? We have the 128, 128. And then we have a downsample, right? That happens after that. And then we're going to have at 256, 256, because there's 2 layers, no spatial changes, no change in anything. All we're doing is changing nothing, actually. We're changing nothing at all in these residual and attention blocks. 256, 1616, 256, 1616. But then we do another downsample. And then we upsample the number of channels, 88, 88. And then we do another downsample to 44. But then the 512, gets upsampled to 1024. And that's basically the pattern that we see here. This is our groupings, assuming we have 2 layers per block. And so this is coming from the encoder, right? Basically this is basically our block 1, block 2, block 3, block 4. These are our 4 encoder blocks. Well, now that we're decoding, we have to go the opposite direction, right? Because we got, for example, we've stored stuff in order of top to bottom, but now we're going bottom up. So we have to essentially reverse the list of the stuff that we've done here so we can concatenate them, right? So we can start from the top. So we're going to basically start from the bottom and work our way up. Our ResNet skip channels, how many channels are we getting from the skip connection? That's going to be equal to in channels if I is num layers minus 1, else out channels. Why is that? Because initially, right, the number of input channels, the things that were, or basically the number of, and let's maybe name it this way. This specific block, block number 4, has 512 input channels and 1024 output channels. At the beginning, right, at the start, we're expecting to concatenate on something that has 1024 channels, the out channels. That's why it says else out channels. But once we've gone through all the layers, then we're expecting to concatenate on something with 512 channels, the input channels. So that's why you see that here. So we're basically checking, are we at the beginning or are we at the end? And it's as simple as that. Now that we have that, we need to actually see what this looks like. So let me paste the pattern in. There is a little typo in this. Let me just fix them real quick. Let me close you. This should be 512 and this should be 256. There you go. So here's the pattern. It's pretty straightforward, but it's just kind of confusing if we don't lay it out like this, right? So the pattern is basically this. This is my input. The output of the mid block is 4 by 1024 by 4 by 4. No problem. But then I have this thing that I need to concatenate on. 4 by 1024 by 4 by 4. And when I concatenate these things together, I'll get something with 2048 channels. So I'm going to have a convolution go from 2048 down to 1024 again, specifically the output channels, right? So there we go. So whatever our output channels are, which is the output of this block was 1024, whatever the output channels are, that's what we're going to go down to. And so we get 4 by 1024 by 4 by 4. No problem. Well, this becomes the input again. And the next residual is again 4 by 1024 by 4 by 4. That's this one right here, which means this 1024, this 1024 concatenate together, 2048, we're back to 4 by 1024 by 4 by 4. No problem. And this, again, becomes the input right here. But now, here is the new thing we're going to concatenate on, right? Remember, we're going in the reverse direction. So this is going to be 4 by 512, 512 by 4 by 4, which is fine. 1024 and 512 add together to make 1536, and we'll project it back to 1024 channels. So we're back to 4 by 1024 by 4 by 4. This just keeps it easy, right? So basically all of these blocks have the same output channels every time we do it. It's just this sum seemed to change once because this changed right here. But here's the problem now. From the next block, right, for the next block, our spatial dimension is no longer 4 by 4. It's 8 by 8. So I can't use this anymore. I can't really concatenate anything to this anymore. So I have to put it through an upsample. I upsample it once and then get my 4 by 1024 by 8 by 8. Now that it's upsampled, I repeat the pattern. 1024 by 8 by 8, I have a 512 by 8 by 8, so I can do plus 512, gives me 1024 plus 512, 1536. I project down to 512 because that's my output channel. And so 4 by 512 by 8 by 8. And then I go to the next one, 4 by 512 by 8 by 8 is my residual. I add them, I concatenate them, 1024, 512, and you can see this pattern happening again. Again, once we get to the very end, well, we're at 8 by 8, but the next thing up for the next block is 16 by 16. So again, I have to upsample it and rinse and repeat, right? This is exactly the pattern that we're going to do. To make this work, we basically have two things that we need to keep track of, right? The first one is, what is my skip channel? How many channels am I expecting to get? And like I said at the beginning, we're expecting 1024. That's the number of output channels, right, of this specific block. At the end, right, when I is numLayers -1, we're expecting 512. That's the input channels of this specific block, because this channel went from 512 to 1024, in channels to out channels. And we repeat that for all of them. So that's the first thing we keep track of. How many skip channels do we have? The other thing we have to keep track of is the number of input channels. How many am I expecting here? This is a little bit easier because I'm always expecting initially 1024, 1024, 1024, but then notice the pattern, 1024, 512, 512, 512, 256, 256, and then 256, 128, 128. So the number of channels I'm expecting to get is dependent on the previous block's output channels, right? The previous block, for example, the number of input channels that this block is expecting, block number 4, is dependent on the previous block's output channels. The previous block outputted 512, so this block is expecting 512. This block outputted 256, so this block, block number 3, is expecting 256, so on and so forth. So that's basically the pattern, and we see that work out right here as well, right? The number of input channels at the very start doesn't really matter, and actually this should be, yeah, this should be fine. And so let's just code this in. So resnet in channels is equal to prev out channels, which we're going to pass in. How many channels did the previous block have? So we're going to pass that in right here, just so it's clear. We're going to use prev out channels if I is 0 at the beginning, else out channels. Because once we've done one of them, right? So once we've gone from, we've expected 256, that's what the previous output did. But these blocks are at 512. They're already at 512, right? So we've already, or let's maybe look at it right here. Let's maybe look at this transition right here. We went from 512 to 512. This is 512, but now we're at 256, right? We're expecting 256 or whatever else it may be. So we just need to make sure we keep track of these things. And this is how we're doing it. We're going to pass in what was the number of channels from the previous block, and then the out channels after that. It's a little bit confusing, but if you study this picture, it should make it relatively clear. And basically that's what I'm tracking here. The number of input channels. The block 1 here corresponds to block 4. This is block 1 in my upsampling. This is block 4 in my downsampling. And these two, this block and this block, pair together. And so this block in my upsampling, right, for my up block 2D, initially expects the 1024 from our previous out, right? So when I is 0, it expects 1024. But then after that, it expects 512, whatever the out channel is, because initially it's going to be 1024, but then after that it will switch, right, to 512. So this is exactly the pattern. Again, over here, initially, this is expecting 1024, but then it becomes 256, right, later on. Okay, or it becomes 512. Sorry, it becomes 512 later on. Again, this one is expecting a 512 out channel, but then after that, it becomes 256, the out channel. This one's expecting a 256 prev out channel, but then it becomes 128, the out channel. So you can see the pattern, right? The first one is how many things did we have previously? And then the next two, or everything after that, is how many things did this block expect, right? So basically, what is the output of this specific block? And we just reverse it around. I hope this pattern is making sense. So now that we have that, it's going to be pretty easy. Self.resnets. And actually, I'll just paste this in because this is the same code as before. Right there. Just delete U2. And there we go. So basically, what we're doing is the input channels to this block is going to be the resnet in channels plus the skip channels. The resnet in channels plus the skip channels. So whatever this says plus whatever this says, this is how we're keeping track of our layers. The output channels is just the output channels, right? Whatever the output channels are. Because that's what we always want to map to. If this block outputted 1024 at the end, right, this block, then we want the first block to output 1024 for everything. If this block outputted 512 at the end, then I want this block, my second block, which corresponds to it in the upsample stream, outputs 512 for everything. Outputs 256 for everything. Outputs 128 for everything. So that's why the out channels is set here. Attention doesn't change the shape. That's just computing attention. And then at the very end, right, if self.add upsample, that's fine. Self.upsample is going to be upsample block 2D in channels equals out channels. Kernel size is equal to upsample kernel size, and then upsample factor is equal to our upsample factor. Should be a factor of 2. There we go. Now for the forward method, pretty easy. X residual block tuple, right? So basically, we should have the corresponding residuals that we need to concatenate together, right, to make this happen. And of course, we're also going to have our time embed and our text conditioning, which is none by default, and text attention mask, which we'll set to none by default as well. So we're going to do for res attention in zip self.resnet self.attentions. We're going to do our skip connection, right? Let's index it. Connection is going to be our residual block tuple dot pop 0. The reason we're popping from the beginning of the list is because this list will already have been reversed. So I've been kind of working my way from the bottom up. Well, we're actually going to work top down, popping from the top of the list because we've already reversed this list. So it doesn't, that's how we'll do it. We haven't done that yet. We'll do that in the actual UNet later, but we'll get there. Torch.cat, it's going to be X, skip connections, dim equals 1. We want to concatenate on the channel dimension. Oh, don't need that. So on the channel dimension, so dim equals 1. And then X is going to be the residual resnet X time embed. And then if attention is not none, X is going to be our attention on X with the text conditioning, and text attention mask. If self, right, if we have the upsample, if self.add upsample, that's fine. X is self.upsample X, and we return X, and we are done, right? That's basically it. So this is probably the toughest part of the implementation. If you're still confused, I would again just come back and study this. So I put all the shapes here, so it's as clear as possible exactly what's going on, right? So you just keep track of exactly, and I just printed this out based on my, I just printed out the shapes here and just kept track of them, and it makes it easy that way. So finally, we need the UNet 2D model, and then module, and I'm going to paste in, actually, this one's easy. So we're going to do def, init, self, and config, right? So we're going to use a config file now, just like we did for the VA here, just to make it as simple as possible. Okay, good. So this is mostly going to be pretty easy. We have one small part that's a little less easy, but that's fine. We're going to see that in a second. Self.convin is going to be nn.conv2d. It's going to go from in channels is going to be from config.latent channels. Remember, it's like a 4-channel latent. So we're going to do from that to out channels equals config.unet channels per block 0. So if we look at our config, we have our UNet channels per block. So we're going to initially take our 4-channel latent and project it up to 320. And that's what this is doing, right? We're just doing that. We're going to do a kernel size is 3, and padding is same, so we don't change the resolution, the height and width resolution of this tensor. So first for the encoder, self.downBlocks is going to be nn.module list output channels is config.unet channels per block, that list of channels per block, and we're going to start at 320, right? So we're going to do for I block type and enumerate config.down block types. What are down block types? If we look, closed it. If we look right here, the down block types is the first block should be an attention down, then attention down, then attention down, and then another one that's just down, no attention, right? So that's what it is. So do we want a down block with attention or without attention? And in the implementation from diffusers, the first 3 down blocks were attention, the last one wasn't. The first up block was non-attention, and then the 3 after that were attention, right? So we're going to just manage that way. So for each one of these, our input channels is our output channels, right? That's our starting point essentially. And then our output channels is going to be config.unet channels per block I, right? Index out which channel are we on. And one thing, just like we had in the VAE, we had defined 4 blocks, right? 4 blocks with these channel numbers, but we made sure that we only downsampled in everything but the last one. So we don't downsample on the very last block. And that's it. So that's the only little extra thing. So we're going to do a flag for that is final block is going to be I is len config.unet channels per block -1. Check, is it the final block or not? Encoder, use attention. Are we using attention here? It's going to be true. And we can do it. It'll be if block type is equal to attention down, right? If we're using attention down, right? If it's attention down, then use attention. If it's just down, then we won't be using attention. There we go. So the block, pretty easy to, sorry, my cat is a little hungry, but I promise I fed her. So we'll delete these 2. And so that's the down block. That's the down block we've already implemented above. There we go. That's the block, and we're going to append the block and store them, and we're good to go. The down block, everything else about is the same, right? Input channels, output channels, we have whether or not you want to use attention, the attention head. Are we doing cross attention? Well, we are, if there's text conditioning or not. The number of layers, transformers per layer, transformer type, just everything that we've defined is kind of rolled up into this one thing. After that, we have our mid block. Right, so what we did right here is the down block. So for the mid block, we're just going to do, actually I can just paste this because this is identical. True, and we'll make it simple. This is going to be if config mid block types equal attention mid, right? So here I just use mid, but if it's attention mid, then there'd also be attention. I could have put attention here as well. I just forgot to. So, and this is mid block types. There you go. Yeah, good. All right. So again, define the mid block. We'll get rid of the class conditioning stuff. And this is the mid block we've already defined earlier, so nothing crazy. Now we have the decoder, and this is where the fun begins. So we're going to self.upBlocks is going to be nn.module list, and then our reversed channels per block is going to be list reversed config.unet channels per block. Okay, so first, we know that as we're encoding the encoder at 320, 640, 1280, 1280, which means the decoder, our up blocks, should just reverse this, go in the opposite direction, right? So that's what we've done here. We reverse the order. And now what we're going to do is output channels is equal to reverse channels per block, 0. And we're going to do for I block type in enumerate config dot up block types our prev output channel, right? So here's the first part, output channels. This is the number of channels of the previous output, starting with the output of the mid block. So when I was mentioning this right here, we pass in the prev output channels, which tells us how many channels am I expecting from previous, right? So that was 1024 here, and then 1024 here, prev output channels 512 here, and then 256, 256 here. So it starts with 1024 because that's what the mid block is outputting. Or in our case here, 1280, that's what the mid block is outputting. But then afterwards, it'll be basically what's the next thing I'm expecting? Well, this block after the mid block, this block number 4 outputted 1024. So that's why it's 1024. This block in the encoder outputted 512. That's why we have 512 here. And then this block outputted 128. So that's why this is 128 here, right? Those are the output channels. But previous output is what was earlier. So this 256 here is what was the previous block's output. This 512 here is what was the previous block's output. This 1024 is what was the previous block's output. And this is 1024 here because that's what the mid block gave us, right? So that's our starting point essentially. So this is dependent on the mid block, but we keep everything the same just to keep it a little bit simpler here. So our previous output channels is just the output channels. This is the channels of the previous output. So this is the prev output channels starting with mid block, right? With the whatever the mid block output is. And now we're going to update the output channels. So we're going to do output channels. It's going to be our reversed channels per block, I, right? So the actual output channels, now we're updating it because remember, this is 1024 prev output, or maybe let's do one in. So 1024 is here, but then the actual output channels of this specific block was 512. So we've gone ahead and updated it, just index it out, right? Because we've already reversed it, it's good to go, so it's 512. Now that we have that, this is the line that becomes a little bit more complicated. So this is the last annoying thing, our input channels. How many input channels are we expecting? It's going to be the reverse channels per block, I plus 1, which makes sense, right? Our input, remember, here, the input to this specific block was 256, and then it went to 512, because remember, it went from 256 to 512, 512 to 1024, so the input is whatever was before, and the output is whatever we're at right now. Now, the reason we're doing I plus 1 instead of I minus 1 is because we've actually taken this list, and remember, we've reversed it, right? So it's actually 1024, 512, 256, 128. So we're at 512 right now. Well, then we're going to I plus 1. 256 is what was inputted there. And this would technically work, except for one small caveat. The caveat being when we're at 128, at index 3, if we do I plus 1, we're indexing outside. We're indexing outside of our setup here. So that's a little bit of a problem, right? Like, what do we do? What's the boundary condition essentially here? And the boundary condition is this. Remember that at the very beginning of our UNet, we implemented this convin. It's going to go from input channels to, in our kind of case up here that we've been doing, it'll go from input channels to 128. This is, let's go back down. Where'd it go? Right here. This is something we're going to be storing in our set of residual connections, our skip connections, which means technically, this 128 is used twice. The first 128 is used for that very first convolution, the output of this thing right here. The second 128 is used for the expected reason, basically all those downsample blocks that we've defined. So our boundary condition should be, once we're at the end, just use that value again, right? And so we can write this in a bunch of different ways. Actually, we'll just use a simpler one. We'll do min I plus 1 or len reversed channels per block minus 1. So either use I plus 1 if I plus 1 is available, or just use the last one, which is the last index available. And of course, on the last iteration, I plus 1 is going to be greater than this. So we're going to end up using this. So we end up using 128 twice, or in our actual model, we end up using 320 twice. And this is, again, because this is an extra output we'll be storing that we didn't really account for anywhere else. So we're accounting for it right here. We'll see that come into practice in just a bit. Next, we have is final block. Just like before, it's going to be I is len reversed channels per block minus 1, right? So are we on the final block? Because just like we had before, we don't downsample on the final block here, so we don't upsample on the final one on the upstream. So we just try to keep it the same. So no upsampling on the last one. And also decoder use attention is going to be if our block type is going to be attention up, right? Is it an upsampling block? Well, there we go. After that, nothing else changes. We just define our block. This time our block being an upsampling block. This should be input channel. Decoder use attention. Don't need U2. And here's our check for if we're not in the final block, then don't use an upsample, right? Just keep it simple. And that's it. And one other thing, one small detail, is why is num layers in our upsample residual layers per block plus 1, but in our downsample, it was just residual layers? Why is there an offset? And I also made a little picture for this. Let me just paste this in. So X, right? X will go, so this is in our downsample block. This is one block. X will go to a residual connection if there's 2 layers, and then a downsample, right? That's the setup. And basically we have these skip connections we've stored from these temporary outputs. But that technically means that we had 2 layers here, 2 residuals, but we ended up with 3 different outputs, which means for our upsampling, we have to do this. We need to store skip 1 plus X residual, skip 2 plus X residual, skip 3 plus X residual. So our downsample may have 2 layers, but it requires us 3 different upsample layers to consume all of these skip connections that we've stored. This is why num layers has a plus 1 here, right? Because we need that extra layer for indexing to work out. So again, there's just lots of little annoying details like this, but that's basically what it works out. And that's why I drew these in groups of 3. These are basically the 3, even though we set num layers to 2 here. Each of these layers will each of these blocks, this full UNet block, will return 3 because we're going to get 2 from the layers and 1 from our potential downsample, right? We're going to get 1 from, or sorry, let's scroll back up. Even though we have 2 set here, we're going to get 2 from here, and then we're going to get 1 from this downsample. And so to consume all 3 of those, we need to make sure, let me put that back, we need to make sure we have 3 different upsample things to consume them, right? To actually use all 3 of them. That's just, again, small details that are less interesting because for the most part, you can just use a UNet implementation from diffusers, but we're just doing this for fun, so it's fine. So that's the num layers. That's why you see an extra plus 1 term here, because we have, even though we have 2 layer outputs from the encoder, we also have that downsample to deal with, and that's why we have plus 1. Good. At the end, once we're done with all of this, we simply have to do one more normalization and a convolution. I'll paste these in as well, so I don't have to type them. Basically, go ahead and normalize. We're back to, we've upsampled all the way, we're at the end, so we're going to have to just go from our 320 channels, right, 320 channels, back to our latent channels, make sure the dimensionality doesn't change, and we're done. So now let's do our forward method, forward self x time embed. We'll have our text conditioning none and text attention mask none. So first, our residuals is an empty list. Store that right there. And we're going to do x is self.convin x, and we're going to do residuals plus equals x. This is that extra thing, extra one that I mentioned here, right? This is why that 128, so going back here, this is why this 128 has to be repeated twice because we technically built all of this assuming the data is coming from these residual and attention connections. But no, we also have this extra one from our initial convolution. Now we're going to do forward block. Forward block in self.down blocks x and skip connection is equal to block. And this is going to take in x, our time embed, our text conditioning, and our text attention mask, right? That'll be basically passing it through every single block. Every one of these down blocks will produce a tuple of skip connection, so we can just append it onto ours. So residuals plus equals tuple skip connections. Just store them all in there. So we're going to end up with basically a huge list of skip connections, and then groups of those skip connections come from basically groups of our blocks, right? From these blocks. So like if we have block 1, we're going to have skip connection 1, skip connection 2, skip connection 3, and then block 2 will have skip connection 4, skip connection 5, skip connection 6, right? For every single block, we're going to have some skip connections. We're going to have to re-index this in a bit, but we'll get there when we get there. X is going to be equal to self.midBlock. This is our mid block. X, time embed, text conditioning, and text attention mask. Go ahead and store that right there. So we have passed data through the mid block. So we've done the encoder, stored temporaries. We've done the mid block. Now the decoder, right? The decoder. So it's going to be for index block in enumerate self.upBlocks, right? So for every single one of these upsample blocks, how we're going to do it is this. I know that, and actually, before I do that, our residuals is going to be list reversed equal to list reversed residuals, right? Because like I mentioned, this is going to be what do you call it? Pre-reversed. There you go. List reversed residuals. But now, like I mentioned, we have a list of all the different residuals from all the different layers and all the different blocks, but we only need a chunk of them at a time. So what we're going to do is this. We're going to basically index out a piece of it. We're going to do a selected skips is going to be equal to residuals from start index to end index. Right, so we're going to just grab pieces of this. Now the question is, how do we figure out our start and end point? Well, that's pretty easy, right? The main idea is we basically just need to do a little bit of slicing, right? We just need to slice this. And the way we're going to do it is like this. Our start index is going to be equal to the index, right? So which block are we currently processing times our self.config UNet residual layers per block plus 1. And our end index is equal to start index plus config plus self.config UNet residuals. Oh, let me just paste this in if I'm mistyping it. There we go. Okay, plus 1. Now, where did this self.config UNet residual plus 1 come from? Well, that's what we did here, right? Residual layers per block plus 1, because we have an extra one for every single up block. So we need to make sure we index that extra one. And we're going to basically, if there's like 3 of them, or if we had 2 of them, and so we had 3, then the first one's going to index from 0 to 3, and then that's basically 2. We need to make sure, though, we add an extra one here, as indexing is not right inclusive, right? So it's not right inclusive, so we're going to put the end index one more extra over so that we actually get the 3 that we want. And that's basically all it is. So that's our selected skips. It's as simple as that, right? We're just grabbing them. And then our x, we're going to pass x, we'll have our block, and it's going to be x selected skips, our time embed, our text conditioning, our text attention mask, and that's it. So again, this is not too challenging. It's mostly just annoying more than hard. because it just takes some effort to make sure you're keeping track of all the shapes and how the concatenation is happening and the patterns. And once you have that, then it's not too bad. And then you have a final convolution output, right? A normalization, a CELU, a convolution. And we are done with the UNet, right? So we'll debug this later when we actually go to use it. For now, though, now that we're done with the UNet, we kind of have everything we need for training our model, or actually writing the final LDM model. So to write the latent diffusion model, this is very simple. So it's basically just a wrapper on everything we've done so far, but there are a few small things that we need to keep in mind. The first one is we need a scheduler. Remember, this is a diffusion model in the end. We're just doing diffusion in the latent space rather than the normal pixel space, which means we need a scheduler. So I've actually already copy-pasted this scheduler from the diffusion tutorial. So if you want to know how to code this, how to build it, and the meaning of it, and more importantly, the derivation behind all the formulas you see here, go ahead and take a look at those videos first. Because I don't want to make this longer than it needs to be, as I've already done a huge deep dive into this. So go ahead and take a look at that. You could also use Hugging Face diffusers, like they have a bunch of schedulers you can pick from. But yeah, we're just doing a standard linear beta schedule to keep it simple. I'm sure there's better ones or better methods, and this is normal DDPM, not even DDIM, but that's okay. We're keeping this as simple as possible. So yeah, here is our sampler. And this is what we're going to use. And just as a recap, what a sampler is it gives us the schedule, the beta schedule. It gives us the logic to add noise to image, some time steps worth of noise to an image, and also gives us the ability to remove noise from our image, right? So both of these things are going to be used, and we'll see them later. Okay, so given this already exists, let's go ahead and write our LDM. So I should be able to paste all of this in. Oh, of course, we're actually missing something. We need our embeddings. Let's go and do that first. Embeddings. So for our embeddings, there's two that we basically need. We need our positional encodings. This is our time step embeddings that tells us our, the time step embeddings, which essentially just tell us which time step of diffusion are we currently on. So we're going to do that first. Import torch, import torch.nn as nn, and then from transformers, import clip text model. We'll need that a little bit later. Plus positional encoding nn.module, and this uses the standard sine cosine embeddings from our attention is all you need paper, right? So you can just use that def init self max len, so 1000, however many time steps you have, time embed dim start, time embed proj dim, and then requires grad is false. We're going to do self max len is, I'm actually going to just copy this piece in, right? Just time embed start dim, there we go. And we'll do self.encodings, self.encodings is equal to self.build positional encodings. Let's go ahead and build those. So it's going to be def build positional, let's paste it, encodings, self, and this is our standard formula. So we're going to create an empty matrix, torch.zeros. It's going to be the shape of max len by self.time embed start dim. And d type is torch.float, just start it off. Our position index is torch.arange from 0 to self.max len. Again, d type is torch.float. And we're going to dot reshape -1, 1. So we've basically unsqueezed -1. We added an extra dimension, so it's num positions by 1. And then our embed dim skip index is torch.arange 0 to self.time embed start dim. Step is equal to 2. D type is torch.float. Because remember, let me pull up the attention is all you need paper. Just pulling up that quick formula. It was right. Where are we looking? Right here, right? So you can see we're basically doing 2 over d. We have every other position 2i plus 1. So that's basically what we're managing here right now. The embed dim skip index. You'll see how that falls, how that's used in just a second. So this is going to be, let's see, encoding 0. Or actually empty, because it's for every position, max len. And then we're going to do it along the embedding dimension, 0, but every other one, because that's what it is, right? So for 2i or 2i plus 1, so every other position, we're going to do 2i divided by the d model and 2i over d model. Okay, so that's fine. Let's do exactly that. We torch.sine, yeah, that's what it is, sine of position index divided by 10,000 to the power 2i d model divided by d model. So 10,000 to the power embed dim skip index, right? Because this is our 2i. It's going every other position, right? As step 2. So 0, 2, 4, 8. Divided by self.time embed start dim. So whatever the d model is the embedding dimension. So there you go. In the same way, I'll paste the rest of this in so I don't have to type that again. Oh. There you go. Yeah, sorry, type it again. Same way, encoding, but now we're going to start from 1 to the end, skipping every other one, right? So it's 2i plus 1, it's cosine, and again, everything else is the same, right? Nothing else really changes. So our sine cosine embed is going to be nn.parameter encoding, and requires grad is self.requires grad. This is optional. Do you want these sine cosine embeddings? Do you want to like initialize them like this and train them? Do you want to leave them alone? It's more standard to leave them alone. Like just don't train them, leave them alone. And our encoding is equal to nn.embedding self.maxlen self.time embed start dim. Encoding.weight is equal to the sine cos. So basically I'm storing these values that I've created inside an embedding matrix, and we can return the encoding, and we are done there. So now, this is pretty standard. It is all optional, but typically in diffusion models, I've seen that we don't directly use the sine cosine embeddings, but we use a projection of them. The time MLP is nn.sequential, and it's just a stack of a couple of linear layers with the GEGLU activation. So it's basically a linear layer that's going to go from the start dim to the proj dim, and then proj dim to proj dim with an activation stuck in between each one. And there we go. So our forward method is very simple. Def forward self time step index, right? So that's what we're passing in. Time embeddings is going to be self.encodings. Grab the embeddings for those time step indexes. Time embeddings is going to be self.time MLP, time embeddings, and return time embeddings, and we're done. That is our positional information. We also need a text conditioner. So let's go ahead and do that. It's going to be class text conditioning condition all embeddings nn.module def init self, and we have some options here. First, pre-encoded text. If text is already pre-encoded, right, like we are for training purposes, then there's really nothing for us to do here. The text is already pre-encoded, we can just use it as is. But if it's not, then we actually need to do something. Text conditional Hugging Face model is going to be the OpenAI clip VIT large patch 14. That's the model I'm using, so you could try you could really use any LLM, but we're using clip here. Text embed dim. It looks like it's 768 by default, so that's what we're going to use. Okay, self.pre-encoded text is pre-encoded text. If not pre-encoded text, if the text is not pre-encoded, like we're not already grabbing embeddings, then we actually need the model. So we're going to do self.text encoder. We'll need this during inference time, but during training time, there's no need to load parameters that we're not going to use, right? So from pre-trained, and it'll be text conditional Hugging Face model. Self.text encoder, throw it into evaluation mode, as this is not something we're training. And we're going to do for param in self.text encoder parameters. We're going to do param.requireScrad is false, right? So just basically turn off. We're not training this. It's just there to embed our text. So now let's do our def-forward self. And what we're going to do is pass in the batch size, the text conditioning, the text attention mask, and CFG dropout prop. So we haven't talked about this yet. This is our classifier-free guidance. So we'll see that in just a second. None. We've talked about this before, but I'll do a recap. Okay, good. So what we're going to start with is a quick if text conditioning is not none. So if we do have text conditioning, and if not self.pre-encoded text, then we're going to assert first text conditioning dot dtype. Dtype is equal to torch.long, because if our data is not pre-encoded, right? If the text is not pre-encoded, so it's not already, we've already done it, but if we haven't pre-embedded it, then the input text conditioning should just be tokens of type long, right? Text tokens. We're going to do with torch.noGrad. We're going to do text conditioning is equal to self.text encoder. Input IDs is equal to the text conditioning, and attention mask is our text attention mask. Right, and what we can do here is a quick small idea. So we're going to do if CFG dropout prop greater than 0. We also add dropout to this. So we're going to do dropout mask. So what classifier-free guidance? The main idea is that we're going to be training our model with text-image pairs, but we would like our model to sometimes not have the text available. So it has to kind of do both. It has to do both conditional image generation, conditioned on text, but also sometimes it has to do non-conditional image generation, which is basically random image generation, where there's no conditioning signal. So we're going to do dropout mask is equal to torch.rand text conditioning dot shape 0, and device is text conditioning dot device less than CFG dropout prop. So what you're seeing here essentially is for every single sample, the batch size, right? So for every single sample, we're going to produce a random number between 0 and 1. And for anything that's less than this, so if this is 10%, which means 10% of the time, anything that's less than this, we're going to drop out. And so now what we're going to do is our text conditioning dropout mask is going to be self.null token. So let's go ahead and produce that. We're going to produce a special token here that just acts as our null token. So basically null token for classifier-free guidance. So null token is going to be nn.parameter. It's going to be torch.rand n, right? Randomly initialize it 1 text embed dim. So it's going to be basically batch size of 1 time step, it's just 1 null token with an embed dim. And we're just going to replace them with this null token, right? We want these randomly selected samples to have no conditioning. So we had text conditioning, and then randomly we've replaced some of that text conditioning with our null token, and that's it. Okay. So finally, our text conditioning is equal to text conditioning plus, and actually this is a hack. So here's a little bit of a problem. DDP, right, our DDP system, explains, distributed data parallel, expects that all parameters have gradients. But technically, this null token won't always be used, right? It may not have gradient. I'm just going to keep throwing a warning over and over again saying, like, some learnable parameters don't have gradient. So what we're going to do, just as a hack, is we're going to do text conditioning plus 0.0 time, 0.0 times our self.null token. So the null token will always get 0 gradients if it's not being used at all. But this way it always gets some information. We don't really care about the null token. We could have just made him, we could have actually just initialized it at 0 and just left it alone. But either way, this way the null token always gets some gradient, like basically the DDP system sees it as getting gradient, but the gradient's always just 0. So this is just a hack. Else, text conditioning is self.null token dot repeat batch size 1, 1. So if we're not passing in any text conditioning, then just go ahead and just use the null token. Right, use the null token, repeat, basically give every single sample in the batch just the null token as its input. Return text conditioning. And that's it. That is our setup. We are not doing class conditioning, so we don't have to worry about that. Okay, we'll have to repeat a little bit of that again for our final inference script, because that's really where we care about all of this, but let's just keep going. We're going to write finally our LDM. So this is where it matters a lot. This will kind of have everything we need for training. So we've also provided, remember the loss function for diffusion is typically mean squared error, but you could also use L1 or Huber or something else, right? So we've put all that here. I don't think we have that util method. Let me grab this real quick. So we're going to go here, utils, save generated images. Here we go. So we'll need this later, but I'll just put it in our util file for now. It looks a lot like the method we already have. Basically, this is a method that, given some image tensors and a path to the folder, it'll go ahead and just do all the same processing as before, rescale from -1 to 1 back to 0 to 55, convert to an image, and then just save them, right? It just saves them all. It's like one nice like image so we can see all of them at once. So there's nothing fancy here. You can take a look at some of these utility codes later. So from utils, save generated. I think that is all I needed. We don't have a VQVAE. That can go away. And we have all of this, and we wrote our scheduler, so I think we're good to go. Yeah, I think we're good to go. All right. Let's go. So we can write our LDM now, nn.module. And the latent diffusion model is just a wrapper on everything we have worked on so far. Self, our config, self.config is config. Self.VAE, right? Our variational encoder, VAE, is going to be our VAE. Config equals config, right? Just pass that in. And what we're going to do is our VAE, the variational encoder at this point is trained, right? This is a pre-trained thing that we start with. So we're going to have to do for param in self.vae.parameters. We're going to do param.requireScrad is false. We're going to just disable it, right? We don't need it anymore. And also we can do self.vae.eval or evaluation mode because we're not training with this model, right? We're just going to be using it for inference. And we're going to do our time step, and actually let's do our time step embedding. Self.signU. I'll just copy this in because I've already written all this. So it's fine. It's just calling the things. We have our sinusoidal time embeddings, the one we wrote. We have our text conditioning, the one we already wrote. So we have everything we need. We also need our UNet model. Self.UNet is going to be UNet 2D model, again, config. And self.ddpm sampler is going to be our sampler. Total time steps is equal to config.num equal config.num. Here, I'll just paste this into. So this is just the ddpm sampler as we have done in the original diffusion video that I did so long ago, right? So again, this is using, I didn't code the sampler, the scheduler, because I've already done this in detail before, so go ahead and watch that video. But here you go, this is the sampler we're using, and we sort of provided how many time steps, the beta start and beta end for our linear beta scheduler. Okay, so now that we have all of that, we have our scheduler, we have our sampler, let's write a couple methods. Def load VAE state dict. There's some helper methods. State dict. This can be success. Is going to be self.vae.load state dict and we can return success. That'll protect, it'll print out whether or not we successfully did it. We need to do a def VAE encode images, right? Self, X, and scale factor, which we haven't talked about yet. We're about to in just a second. We'll get there. Whenever we encode an image with the VAE, well, we should do it with torch.noGrad. No gradients necessary here, right? And so we can just use our VAE method from before. Return self.vae.encode x. Return stats is false. We don't need any of that. And scale factor is our scale factor if we pass it in. And all we need is the posterior, right? So this is basically Z, the latent space. In exactly the same way, we need to be able to decode, right? So VAE decode images and pass all that in. Good. And finally, we need to be able to write our standard forward method, self images, text conditioning, our text attention mask. Let's set these to none by default. Let me put them in different lines so it's clear. We have our scale factor is also none, and our CFG dropout prob is 0. Right? So that's our class. With what probability do we want to randomly remove the text conditioning? Right? That's basically all it is. So what we're going to do is if self.config.textConditioning, text conditioning is equal to self.textEncoder, batch size is equal to images.shape0, or I'll just paste these in so I don't have to type this actually, right? This is just the methods, the forward methods we've already written. Just grab the text encoder, pass in the stuff as needed. This will also do the random dropout of our conditioning based on the dropout prob. After that, we need our compressed image. So compressed image is equal to self.vae encode images, and scale factor is our scale factor. Now here's the important part. We've taken an image and compressed to the latent space. The important part now is we want our model to add noise to it and then do the whole diffusion process to it. So first we need to sample time steps. Remember, we have to ask, or we have to randomly sample, how many time steps of noise do we want to add to the image? So we're going to do rand int anything between 0 and self.config.num diffusion steps, right? So that's how many steps of noise we want. And images.shape0, basically the batch size, right? Just we want to sample some number between 0 and 1,000 for 0 and 999 for the 1,000 steps we have, 1 per sample. And this is how many time steps worth of noise we're going to add to each of those images. So then we're going to do our noisy images and the noise we added. So we're going to have the noisy images, right? Basically noisy compressed images, and the actual noise we added is going to be equal to self.ddpm sampler dot add noise. It'll take our compressed images, and it's going to take the time steps. Okay, how many time steps with the noise do we want to add to our compressed images? And that's our noising step, right? We've noised the images. Now we need our neural network to undo the noise, right? So first, let's get our time step embeddings. This is going to come from our self.sinusoidal time embedding, time step .2, and make sure it's on this correct images.device. This happens on the CPU. Didn't need to do it on the GPU. So now we're moving into the GPU here to get our time step embeddings. And then our noise prediction is going to be self dot, and I'll just paste this in. The whole job of the UNet, right? The goal of the UNet is to predict, given some noisy image, predict the noise, right? Given some noisy image, which we've added time steps worth of noise to it, predict the noise that was added to it. That's the entire purpose of the UNet. And then loss is going to be the loss function, self.config.diffusion loss function, whatever you want, mean squared error, whatever else it may be. And we want to do it between the noise prediction and the noise. And we're going to make sure it's .2, noise pred.device. Just make sure it's on the correct device, and return loss. And that's all we need to do to train our model. Basically, again, recapping, we pass in everything. we grab our text conditioning if it's there, go ahead and compress the image. This happens without gradients, right? Because we're not training the BAE. Sample some noise, or sample some time steps, add that many time steps worth of noise to the images, and then go ahead and grab our time step embeddings for those specific time steps worth of noise that we added. Ask the UNet to predict what is the noise that was added to this latent space, and then the loss is just go ahead and mean squared error or whatever between them. Let's similarly just go ahead and write our inference script right now, even though we're not there yet, just to make it simple. So torch.no_grad def inference self. All we need for inference is text conditioning. Conditioning. And I'm assuming single sample inference, not batch inference, just to make it simple, right? Text attention mask is here. I'll just paste this. Should be fine. Right, just all this stuff, standard stuff. So we're gonna do if text conditioning is not none. Right, then we're gonna do model is our clip text model, and I'll paste this. These are just during inference time. I mean, we could have used this stuff up here, but this way makes it easy, right? Just go ahead and just load things as needed. Model, and then we can do our standard model.eval, right? Grab our model, grab our tokenizer, because I'll be passing in text string here instead, right? So we're going to go ahead and make sure there's, I don't know, random white spaces or something like that. We're going to go ahead and tokenize our text. Remember when we tokenized it, we truncate it to max of 77 tokens. That's what the Stable Diffusion model uses, or clip model uses. That's what we're going to do. And then we have to take these tokens, grab the input IDs, the tokens themselves, move it to the GPU, and add a batch dimension. So this will end up being basically one batch dimension. There's only one sample, 1 by L, the length of it, where L is something less than 77. And then we can do with torch.no_grad text condition. I guess it doesn't really matter, but text conditioning is equal to model input IDs dot last hidden state, and this acts as our conditioning signal for generation. Otherwise, if if text conditioning is none, then we can do self if self.config.text conditioning. So if we didn't pass in any conditioning information, but this model supports text conditioning, then we're going to do our text conditioning is equal to self.textEncoder.null token, right? We'll just use the null token as our, hey, we're using our text conditional model, we're just not using any actual text, right? Our latent resolution, remember, we need to basically sample some noise. So here was the size of the latent resolution. It was the image size, 256, divided by 2 to the power number of blocks we had, minus 1. So we had 3 blocks, so it's 2 to the power 3, 8, so it's 256 divided by 8, which is 32. So our latent resolution and our model is 32. And now we will go ahead and sample, right? Sample some noise in the shape of the latent resolution. So it's 1, considering 1 sample generation by latent channels, 4 by 32 by 32. And now the generation process for T in TQDM, torch.flip, torch.arange, self.config.num diffusion time steps, dims equals 0 for the flip. Basically, we generated torch.arange will make something from 0 to 999 for 1,000 steps. But when we do diffusion, right, or inference diffusion, we'll start at 999, then 998, 997, 996. So we're going to go in the reverse order. So we flip it around, right, along. There's only one dimension, so there we go. Our time steps is equal to torch.full is unnecessary, but it's fine. Basically, it's going to be a single number with the number t in it, .2 device. So there you go. It'll be basically a single value with t, right? Whatever time step we're currently on. Time step embeddings, yeah, is equal to self.the sinusoidal time embeddings with the time steps, right? So grab that time steps embeddings. We can now predict the noise. So let me paste that in here, right? Noise spread. Take the image, which is currently all noise, And then we have our embeddings. This is the noise level. This is our text conditioning. We have no class conditioning, right? There's the text conditioning, its mask. And then our image is going to be self.ddpm sampler dot remove noise image t noise spread dot detach dot cpu. So all we're doing here is our ddcpm sampler then looks at the image, looks at how many time steps of noise has been added to the image. In this case, it's all of them, 999. Here's our prediction of the noise, and we remove the noise, again using all the formulations here, which I've derived, and you can take a look at elsewhere. So that's our image, and we just loop this, right, over and over again until we're done. But remember, this is not really the image. This is the latent image, right, that 4 by 32 by 32. So our image is really going to be self.vae decode, because now that we're done doing diffusion in the latent space, we can move it back to the image space, right, back to the pixel space. And then we can do return image. And that's it, right? Pretty straightforward. So our inference script is honestly not all that different from before. We can delete you. I will just not save you. I'll just print you later, so that's fine. And that's fine. We'll just keep it simple like that. Okay, so we have our latent diffusion model done, which means I think we're good to start training. Let's double check. Stage 2, so we're gonna make a new file. Stage 2, diffusion trainer.py. I'm gonna paste in all the usual stuff, all our usual imports. This is just to help if you're getting stuck somewhere. We don't need you. And we will write you in just a second. Actually, let's put you in right now. So in here, what we're going to do is this is load text encodings. So like we had, we want to be able to, as the models as our models training, we'd like to just have some results on some provided texts, right? So we're going to put that in here. So we're going to in our utils. Basically, it's just going to load some lines of text, tokenize it, get the conditioning signal, just so we can inference a little bit later, right? So that's it. It just creates some text conditioning. Just create some text conditioning, grab the embeddings, that sort of stuff. So for this, all we really need is some examples, right? So I think I have some right here. Source maybe? Nope. BABB sample inputs. Here we go. So let me create a new folder called inputs. And inside here, we're going to create a file called sample text conditional prompts.txt. And it's just that, right? So I have some prompts here, and basically I want to use these prompts, and every couple, however many iterations, I want my model to generate pictures of this stuff, right? That's all. And that's what this is doing. This is just loading the prompts and grabbing those text embeddings, so we can then go ahead and use them over and over again as we're training. Anything else? I think we have everything else. Modules. Oh, right. So in my modules, I need in the init from .ldm import ldm. We'll find out if we have bugs soon, so we'll fix them as we go. And we have all our standard experiment name, weights and bias, working directory, logging, training, and model config. We have the path to the VAE backbone because we need to train the VAE first and then use that as the backbone, and then everything else. So we are good to go. All right, training is pretty straightforward, just like every other training loop. Actually, this one's much simpler than our previous one. So because there's no extra stuff, we're just doing mean squared error as our loss function. So just like before, we're going to load some of our training arguments. So again, we have in our configs, we have our diffusion train, and this is the setup for diffusion train. All the things we care about for diffusion, standard training stuff, all that, right? Nothing crazy. Okay, so there we go. With open, we're going to grab those training arguments. We're going to grab our model arguments. Remember, in the LDM, we describe everything. We have the UNet and the VAE all in one place. So we're going to need all that. And we're going to have to come back to that in just a second. That'll be the last thing we do before we train. OK. We're going to do our path to, maybe it won't be the last. I'll probably do it halfway through here. So experiment is equal to os.path.join args.working directory. And actually, you know, I'm going to keep this short and simple because this training loop is not that interesting. We're going to set up the accelerator just like always, right? So working directory experiment name, load the accelerator. We're going to make sure that as we're generating stuff to save, that save directory exists, right? Just so that path exists. So there we go. And then we're going to load our config, right? Load our config. And this will just load our models, and our LDM is good to go, right? That's all it takes. Here is where it gets interesting. The VAE unit variance scaling. So this is not something we've done yet, and I kept mentioning the scaling factor, whatever else it may be, but it's time to finally talk about it. When I train my VAE, I hope that the latent space here has roughly a mean of 0 and a variance of 1. That's ideal. But of course, it's not a hard constraint, it's a soft constraint. So that may not actually be the case. And so in the stable diffusion, let me find it, 0.18215 or something like that. There's this weird constant. Let me see if I can find the exact code. So here we go. Here's a Hugging Face post about it. There's this weird thing they do where they divide the latents by this weird constant, 0.18215, and it seems to come out of nowhere. But the reality of it is this. The latent space, although we want it to be a variance of roughly 1, it never actually works out that way. But we can, because we assume it's Gaussian, we can just scale it to what we need. And so what we need to do is compute our own constants. So let's go ahead and do that now. We'll see what it is, and then see what we need to multiply by to change. So we're going to do new compute VAE scaling.py. This is relatively straightforward. So I will just copy it and paste it in so we can just look at the code. The code is very simple. Basically, what we're going to do is we're going to load our VAE, load the weights of the VAE, load our data set, of course, right? Load our data set that we want to work on, in this case, conceptual captions or whatever else it may be. And then what we're going to do is grab batches of data. And what we're going to do is store the sum of the pixels and the pixels squared. And by looping through the data, and this is basically an iterative way. We want an iterative way of computing the mean and the variance and stuff like that. And what it ends up doing is when we run this, it's going to print out for us what is the actual variance of our latent space, right? That's what we're looking at. We're computing this for the latent space. What's the actual variance of the latent space over the whole data set? What's the actual mean of the latent space over the whole data set? And what we really care about is the variance of that latent space, right? This is just your standard way of like, what do you call it? Iteratively computing the mean and variance of large data where we can't fit the entire data set in our model and in our memory, right? So once we do this, this is going to spit out a constant, right? It's going to say that, hey, this is the variance that you have. And the closer your constant is to 1, the less change you need. But we need to make sure that we can scale. We're going to get some normal AB, right? Whatever. The mean will be something and the variance will be B. We'd like our variance not to be B, but to be 1. But we know that if we divide a normal distribution by the square root of constant, then that divides the, it'll divide our variance by the square of that constant. So this will basically end up being b divided by the square of the square root of b, which is b over b, which is just 1. And that's all it is, right? So we're going to loop through our data and just compute this stuff. And just compute it. And so let's give this a try. Let's see if this will let's see if this works. Right there. Okay. So we're gonna pull you in. Okay, we're gonna do Python compute VAE scaling. The path to pre-trained weights is going to be our, let's see, it's going to be in our work directory. We're going to look in the VAE conceptual captions model.savetensor. The data set will be conceptual captions, and the path to data set will be, let's see, the path to data set will be this. Let's see if this just works. Okay, let's give it a second. Okay, looks like I actually have a couple bugs, so let's make sure. Oh, of course, I don't have any class conditional, so let's make sure I fix all this up. In ldm.py, let's look in there, modules, ldm, there is no class conditional, never implemented that. And actually, I don't even need this to be on 2 lines, so we can clean it up. There we go. Collate function batch must contain tensors found data set. All right, we'll check that in just a second here. Print data set. Let's make sure this actually prints out correctly first. There might be a data set. This should be data set and then collate function. There we go. Okay, and then this data loader should take a collate function. Okay, let's check now. Okay, yeah, there we go. So it's going to loop through. This takes a little bit of time on a giant data set like conceptual captions. It's probably unnecessary to process the entire data set. We could probably just process a large chunk of it and say that's enough. But basically, this is what it's going to do. So let's maybe do step counter is 0, and let's do if num batches. What is that set to? Let's do it that way. Let's set num batches to, let's say, 10. Just whatever, right? Just making up a number. Basically saying I want to process 10 batches and then compute my constants from there. Just so we don't have to process the entire data set, otherwise it takes too long, right? So we'll let this process its 10 batches. And it's going to print out some number. There we go. So this is the constant that it computed from the 10 batches. So basically, what I need to do to make sure that my data is kind of closer to normal is by basically having this closer to 1, right? Having my overall variance closer to 1 is by multiplying by this constant. So let's try that. Let's just multiply it right here. We're going to do this times this constant. And let's see what my average ends up being, or the, not the average, but the variance ends up being over at least these 10 batches. I did it for slightly more data, so the constant's a little bit different, but the constant they computed, again, for their model was 0.18215, something like that. Right, so that's closer to 1. And so you can see it's just a rescaling, right? But remember, this rescaling is being added post-training, right? So in my VAE, in my actual training method, because I'm adding in this random scale factor post-training, I also need to make sure I remove it before I decode. Otherwise, it doesn't really work out, right? So my diffusion model will be trained on scaled data, but I need to make sure I unscale it. That's why you see Z over scale factor before we actually decode, right? That's the key idea. Okay, so now that covers our compute VAE scaling, let's go ahead. I've already stored in my configs here, in the LDM configs, the scale factors I computed for my different data sets, right? So you can see 0.90 is actually pretty close to what we just had, right? These are my constants that I computed. Okay, let's go ahead and continue on our training loop. So what we need now is stage 2 diffusion trainer. Here we go. All right, I'll just keep pasting as I go because this is mostly housekeeping, and then when we get to the actual training part, it'll be fine. So we load our model. We have our scaling constants, which I've already stored for this specific data set, right? So that's what it'll be. And I can set it right here. So there's a couple ways I made it available. Basically in my config right here, I made sure that in my data class config, right, I made sure that the VAE scale factor is available. And if I set it here, then it'll be applied in the model in the way that I implemented it, right? So that's the easiest way to do it. So we can do it exactly like that. Where are we? Stage 2 diffusion training. There we go. Let me actually close out on some of these extra things that we don't need right now. And yeah, in the VAE, you can see I can load it self.config.vae scale factor. If it's not none, then use that. So that's where I'm loading it from. Easy way to do it. And there we go, right? So we're just grabbing it for this specific data set, and we're doing conceptual captions. So this args.dataset will be conceptual captions. Okay, and then we have config.class conditioning. We set it to none by default, and our sample class, or not class conditioning, sorry, config.text conditioning is none by default, and sample text conditioning is false, right? And if our data set, which it is, conceptual captions, if args.dataset is conceptual captions, then this is true. Pre-encoded text is this, and then we load our sample text embeddings from that sample file that I made earlier. So because this is always true, because we're only doing it, I'm going to make it like this. Just keep it simple. There we go. So we load them. Similarly, we need our loss function, right? So config.diffusion loss function, just set it there. It's going to be based on the loss function set in the training config, which I believe by default was mean squared error, right? So that's what we're going to be using, mean squared error. Good. And after that, very simple, go ahead, actually load the model, right? So load our LDM model based on this config. Load the VAE backbone, right? That's our simple code. We have the path to the, we have the path to the weight. Load that, load the VAE state dict, and then send it to the correct GPU. We can print out how many model parameters we have, no problem. There we go. We need to prep our data set. This will look identical to what we had done earlier, but the only thing that really changes is now, well, we don't have this, first of all, no class conditioning. And the only thing that changes is now if we're doing text conditioning, which it will be true, then we will also return the captions, right? We'll get both of them. We can get our data loader then is just a rep. So sorry, I'm just pasting stuff because you don't need to see me type this stuff out, right? So there we go. Because we've already written all this code, it's just little wrappers, right? We have our data loader, there we go. In the same way as we did last time, how many effective epochs are we training for? Depends on how many iterations we set it up for, so we'll see that. We have only a single optimizer. There's no GANs or anything like that. Now it's standard diffusion training on that latent space alone. So there we go. And then we can go ahead and grab our scheduler, right? Grab our scheduler, set it up, and then prepare everything as per accelerator. We can then finally just do the last couple housekeeping things. We can resume from checkpoint if we need to. We can get our latent space dimension. We need this a little bit later just for some sampling. And then we can have a progress bar. All right, so let's now start. While train, right, now that the boilerplate is out of the way, this is very easy. For batch in data loader, we're gonna do a prep batch. It's gonna be an empty dictionary. And we're gonna do prepped batch images is going to be our batch images.to accelerator.device. Move it to the correct GPU. Our prepped batch text conditioning is equal to batch text conditioning. Yeah. If, and here I'll paste this too so I don't have to type it all out. No one wants to watch me type, so this will be that. Just like that. Right, text conditioning, if text conditioning is available, otherwise none. Attention mask, if attention mask is available, otherwise none. And then of course we have our classifier free guidance, right? The dropout probability basically on the text conditioning. So there we go. That's our prepared batch. We can do with accelerator dot accumulate model loss dot model, or sorry, loss is equal to model, and we're going to just pass in that prep batch, and that's it, right? Because we've prepared the dictionary here, pass it in, and we wrote the forward method of our LDM such that it returns just the loss, right, as we wanted. Accumulated loss is going to be plus equals loss divided by training config gradient accumulation steps, right? So however many steps we wanted, we'll just average it out. Accelerator dot backward loss compute our gradients. If accelerator dot sync gradients, then we can do accelerator dot clip grad norm model dot parameters 1.0 standard gradient clipping, and then optimizer dot step lr scheduler dot step and optimizer dot zero out the gradients. Yeah. After that, we can do logging essentially. If accelerator dot sync gradients, then we can do our loss gathered. Here, I'll just paste this in because it's just logging stuff. So go ahead and average up the losses across all the GPUs. Go ahead, right, that's what this is doing. Go ahead and log it, print it to console, log it to accelerate, and then iterate, right? We've completed one step, we reset our loss, and we update the progress bar by 1. If completed steps percent is divisible by training config val generation frequency equals 0. So basically every val generation frequency, we want to just generate some images, right? And that's relatively straightforward because we already wrote a lot of the code for that. So we're going to do if accelerator dot is main process model dot eval unwrapped model is equal to accelerator dot unwrap model, and we're going to do our text conditioning is going to be equal to our let's see here. We actually don't need to do any sampling because we already have text conditioning. So we can do is equal to sample text embeddings. Here, let's do it this way. If sample text embeddings is not none, so if for some reason we didn't pass in some text embeddings right over sample text embedding. So if we didn't do this for some reason, then we could handle it, but we are doing it. So maybe I should just simplify this even more. Sample text embeddings. Yeah, okay. So if it's not none, which it won't be none because I'm actually doing it, then it'll be text conditioning is equal to sample text embeddings, and we're going to grab the text conditioning .2 accelerator .device, and then our text attention mask is going to be again sample text embeddings text attention mask .2 accelerator .device. There you go. So we're going to go ahead and grab them because in our utils when we created them, right, it was these two, text conditioning and its attention mask, and that's what we needed, right? So there we go. That's all we need, and I think that's all we're going to have to keep it as. And our latent is going to be torch.random, right, len text conditioning, and our latent spaced in, right? So it's going to be the batch size by our remaining latent space dimension, which we saved up here somewhere, right? It was, there you go. It was latent channels 4 by 32 by 32, and then we have the batch dimension right here. So we're just going to generate some noise, and we're going to go ahead and do our entire process, right? So now we can do with torch.no grad, And this is the code we just wrote earlier, right? So I'm just going to paste it in again. Nothing different from what we've just done, right? So for every iteration, we're going to flip it around. We don't need to print out a progress bar for non-main GPU, right? So there we go. We don't need class conditioning. And then we go ahead and do our t's will be torch.full for all the samples in the batch. So it's the same t. So it's going to go 999 for all the samples in the batch, 998, 997, 996 as we do diffusion. And then in the end, we're going to do our noise pred will be our unwrap model.the UNet, pass it in, and then we can use our DDPM sampler to remove the noise from the latent and just repeat this over and over again until the denoising is completed. Once we're done, we can go ahead and put our images, unwrap model, VAE decode images, right? Just go ahead, take our latents. Oops, gotta tab out one. The final images is gonna be the decoded latents, right? And then we can go ahead and just save those images using that quick save method that we wrote earlier, or copy pasted in earlier. Model dot throw into training mode. I forgot. Yeah, we have evaluation mode. And then we're going to do accelerator dot wait for everyone, right? All the other GPUs should just be sitting around and waiting until this generation process is done. And then once it's done, we can keep going. And then at the very end, of course, a little bit of checkpointing, right? Just go ahead and checkpoint our model. And that's basically it, right? Very, very simple training loop. It just looks fancier than it is. Let's go ahead and let's see here. I'm going to move over to my main repo because we've written all the code at this point. So I just want to show you that, let's see, bash scripts stage 2 diffusion.sh. This just has all of the scripts that I care about. So we can just start from there. So yes, it's going to use some scaling constant, whatever it is. And it'll train. And I set this to train essentially. If we look at the training loop, I set it to train for, okay, there we go. Killed it. Okay, so yeah, it just takes a while. You can see this is actually a really big model. It has 1, 2, 3, 1, 2, 3, 1, 2, 3. It has almost 800 million parameters, right? Now, you might be asking, how am I able to train an 800 million parameter model but not max out my memory, right? Look, I'm only using 50% of my total memory usage. The reason this is true is because this is the entire point of latent diffusion. It makes the diffusion process cheaper. When you train neural networks, the expensive part is typically not the model parameters. It's not the number of parameters you have. It's all those intermediate activations. So, for example, in our figure here, scroll down. If I was training a diffusion model on these large images, every single one of these blocks in the convolution and these convolutions in the UNet would have like 256 by 256, 128 by 128, 64 by 64, like, relatively large image resolutions. But now each intermediate output is like 32 by 32, 16 by 16, 8 by 8, 4 by 4, super, super, super tiny little tensors. And this allows me to train big models because the main memory cost for training big models is always the intermediate memory allocations. And we just don't have large intermediate memory allocations anymore because our tensors are small, the images are small. So latent diffusion models are way cheaper to train at this stage. Training the VAE is still expensive. This is one big headache that you have to go through. But once you have that, you can pretty quickly iterate on different diffusion models, different diffusion types, things like that, and just train them relatively simply because the memory cost is not nearly as high, right? Which is awesome. So this is essentially the latent diffusion model. What we want to actually do, though, what we're interested in, is our inference, right? Inference. So let's just open up the main folder because I don't want to. We're kind of at the end here, so I know it's a lot of code, but it should have given you a pretty good overview of how these architectures work. Let's go write inference LDM. Here we go. Very simple function, just like it's just like the inference VAE that we had from before. It's a very simple method. And all we're doing, I keep doing that, all we're doing is using that model.inference, right? We already wrote an inference script, right? In our LDM, we already know how to inference. So let's just go ahead and do that. So we're going to do a quick model.inference. We're going to do Python inference LDM, and we're going to give it the model config, which is going to be in config, and it was, let's see, stage, actually it's just ldm.yaml. After our model config, we pass it our path to weights. This was in workdir, and we're going to do, let's say, the, our diffusion conceptual captions, model.saveTensors, right? That was the path to the weights. And then we're going to give some text conditional, right? This is a text conditional model, so we're going to do text conditional just as a flag. Whether or not this model is text conditional, I just pass it in right here. The scale factor is handled already by the data set, so we need to provide it that as well. The training data set is conceptual captions, right? Conceptual captions. And then the prompt, right? This is a text conditional model, so prompt. Now let's just ask it a, I don't know, sunset. Show me a sunset at the beach, right? Sunset at the beach. This is going to take a second. It's going to inference. But basically, this loaded the weights. And now during inference time, remember, there is no this. During inference time, we don't care about any of this. All we do is we generate some latent noise here, and we do our diffusion process in the latent space, and then the decoder generates our image. So this is what we need for inference time. During training time, we don't care about any of this. What we do is we take an image, compress the latent space, and then given the text conditioning, we ask the UNet model to learn the latent space, right? Basically learn to generate the latent space. So here we go. That looks kind of okay. Let's try it again. Again, these models are really hard to get as good as some of the, the hardcore image ones that you see online these days, just because like I don't have 1,000 GPUs lying around. Let's see. Let's just use one of my, I don't know. Let's use one of my inputs that I had right here. Let's see what it looks like. A snowy mountain range. Sure. Let's see what that looks like. So yeah, this will, again, just take a second, generate a single image, and we'll be able to see it. So we can see another thing, right? Diffusion is still expensive. We still have 1,000 steps of diffusion to get through. This is why DDPM is not as preferable to methods like DDIM and things like that these days, but maybe we'll do that in a different video. This was just to talk about latent diffusion in general. Okay, let this get through. I bet if I torch.compiled it, it would actually go a lot faster, but it's fine. Not today. I don't want to mess with stuff. It looks okay. It doesn't really look like a snowy mountain range. Now, what you do notice here, it is a mountain range, which is kind of cool, and it is a sunny sky. You do notice that we have this artifacting, or not artifacting, but like this, I don't know, watermarks. And that's because this is kind of the important part of large or high quality training data sets. So let's kind of wrap this up. Here's some examples. So some example generations. Here's some example generations of unconditional generation from the Celeb HQ, so unconditional generation. Here's some examples that I picked out from my prompts. So beautiful sunset at the beach, foggy magical forest, a futuristic city skyline, and a coffee shop with books. So these are kind of looking like the things that they're supposed to, but obviously not stable diffusion level. But this actually shows up all the time. Clean training data matters quite a bit because we have these watermarks showing up. And this is why data sets like this exist, like much larger data sets like Lion aesthetics. These are like quote unquote images with high visual quality, right? So it's a collection of data with higher visual quality, and there's a bunch of filtering processes to make this work out. And you can see these are actually very much larger, like billions of images compared to just the 3 million that I worked with. Either way, that is it. That's basically the implementation of Stable Diffusion. We spent all this time, again, just as a recap. You train this once, and then this part becomes super cheap to do afterwards. That's basically the big takeaway. So we still have more to come. That'll be an end of latent diffusion. I'm thinking about doing a DDIM or something like that in the future. So I'll think about it. So I will see y'all in the next one.